Welcome to the equilibrium constant. So let's examine a generic reaction. So we have some species A reacting with some other species B to give us some third species C and a fourth species D. And we have J, K, L, and M, which are the coefficients for A, B, C, and D respectively. So note here that we have an equilibrium, so we've got this double-headed arrow showing that both the forward and reverse processes are occurring. So the concentrations of the reactants A and B and the products C and D at equilibrium have to satisfy the equilibrium expression. Now the equilibrium expression is given here, where we have K. K here is called the equilibrium constant. So we have K, that's a capital K by the way. K is equal to the concentration of C to the nth power, remember L was the coefficient on C, times the concentration of D to the nth power divided by concentration of A to the jth power times the concentration of B to the kth power. So note here that our equilibrium constant K is usually expressed as a unitless quantity, regardless of whether or not the units fully cancel. So if L, M, J, and K are all, say, 1, then the units in the numerator and the units in the denominator would be the same, because our concentrations are, say, in molar. So we have moles per liter times moles per liter divided by moles per liter times moles per liter, let's say. But even if they're not, even if the sum of L and M is not equal to the sum of J and K, then usually we express our equilibrium constant as a unitless quantity, even though you as the student or the user of the equilibrium expression or the equilibrium constant K, you should recognize that there are some units there even if we've written it unitless. And we assume that you can understand what those units really are. They really are some unit of concentration. In most cases, we're going to use molarity, so the unit would be molar or molar to some power. Molar squared, molar cubed, molar to the power of -1, -2, something like that. So it's up to you to know what the units really are. So the value of K then depends on the temperature, but nothing else. That means that no matter what the initial concentrations of our reactants and products, the value of K, our equilibrium constant, is fixed at some fixed temperature. So if we change the temperature, then the value of K may be a different value, but at some temperature. So if we're fixing ourselves to only be talking about standard temperature and pressure, let's say, so if we're looking at 0 degrees C, then it doesn't matter what our initial concentrations, how much A, B, C, or D we start with, the value of K is the same. And that means that at equilibrium, no matter what amounts of A, B, C, and D, or what concentrations of A, B, C, and D we've started with, the value of this fraction, the value of this expression, has to be some value. It's got to be equal to some constant. Now again, the value of K can change with temperature. So when we're reporting the value of the equilibrium constant, we need to report what temperature we measured it at. So now let's talk about equilibrium position. Equilibrium position is the set of concentrations of reactants and products at equilibrium. So the equilibrium position depends upon the initial concentrations of the reactants and products. But remember we said the equilibrium constant did not. Now that's because the equilibrium constant is, let me go back here, the equilibrium constant is this guy. The equilibrium position is the values that we're plugging in here inside these brackets. Right? That, the set of those 4 numbers, that's the equilibrium position. So let's say we start out and with 2 flasks, and in one flask we have a little bit more A initially. That means that at equilibrium, to get the same equilibrium constant, which we know we have to have in 2 flasks, we're going to end up with a little bit more A at equilibrium than we do in the other flask. And that means that we're going to have a little bit less of B and a little bit more of C and D in the flask that we started out with a little bit higher concentration of one of our reactants, the A. And so the equilibrium position, this guy, that's the set of those four concentrations, or however many concentrations are involved in the reactants and products. So the equilibrium position and the equilibrium constant are not the same thing. So the equilibrium positions in our two flasks would be different, but the equilibrium constant would be the same as long as our flasks are at the same temperature. Okay, so again, the equilibrium position depends on the initial concentrations of our reactants and products, but the equilibrium constant does not. So that was the equilibrium constant.